Good morning. Welcome to the first of the Let's Calc videos, where we're going to be going through particularly difficult or interesting or even just kind of expandable questions from the problem sets from AP Calculus AB this year. We're going to start with the first problem set, the limits basic assignment, and so we're going to jump right in and let's go look at the first couple problems and write some video solutions out. So the first question we're going to look at is question number 3. And it says in the directions for 1, 2, 3, and 4, given the table of values below, conjecture an approximate value of each limit respectively. So what you're given in this case is a numerical presentation of a function. And you're given some function values around a particular x value, and then you're asked to speculate about what you think the actual limit value would be. So in other words, what's the behavior of the y values doing in that particular region. So in our first example, number 3, or our first question we're going to address, number 3, it asks us to evaluate the limit as x goes to 2 of f of x. And again, it just wants an approximate one, so anything I come up with might be slightly different than yours, but we should be in the same ballpark for sure. This should be in the same neighborhood to use more limit terminology. So in looking here, we're given values of 1.9, 1.99, 1.999, and then on the other side we're given 2.1, 2.01, 2.001. In addition, we're told the value of the function right at 2. Now I know it's tempting right off the bat to just look and go, well, f of 2 is 4, so done. But unfortunately that's not true. We're going to find and talk about even later on in this video that there are many situations where a limit's value does not actually equal the particular function value. If there's a discontinuity, you might have something happening. And that's actually what's happening here in example number 3. So let's look. So as we look at a limit, we want to make sure that we have consensus from both sides, that both sides are going towards the same y value. So let's see if we have that. So in this case, as we look, for f of x, as x gets closer and closer to 2, f goes from 0.3 to 0.33 to 0.33. I might be willing to speculate that if we got even closer, it might get closer to 0.333333. So basically, I would say something like from the left. So if we're looking on the left side, looking at all those values less than 2, it appears that f is approaching 0.33333, etc. So it looks like it's going towards 1/3. That would be my speculation. It's a terrible 3. There we go. 1/3. If we look from the right, in other words, if we look at the values when x is greater than 2, let's see what f is doing as well, or what the y values are doing. So in this case, 0.36, then we get a little closer, we get 0.337, get a little closer, we get 0.334. So again, this isn't perfect, but it sure as heck appears to me like it's reasonable to say that f is approaching 0.333, which means that it also looks like from the right side we're approaching 1/3. Now specifically, although this isn't actually relevant, at x equals 2, we can see that f is literally equal to 4. And so that might, as I said earlier, give you some pause and make you think that maybe you've done something incorrectly here, or maybe we don't have a handle on what the limiting behavior is doing. But in fact, our situation appears to be something like this. We've got a function that's approaching 1/3 from the left side. It's also approaching 1/3 from the right. Technically, it's going from larger to smaller. At that point, though, we don't have instead of having 1/3, we seem to have at 2 that the y value is 4. So what we have is an apparent removable discontinuity. But of course that doesn't change anything. Our limit still exists because both sides are approaching the same y value, which means that I would say that our limit value would be approximately equal to 1/3. Now of course if you wanted to argue that it was 0.33314, I could not stop you. Like technically that's just as accurate, but for the moment 1/3 looks like a reasonable estimate. And again, that that removable discontinuity doesn't actually change anything about our limit value. And again, we'll talk more about that later. Again, this is just laying foundation and helping explain things with a little more depth. So moving on to number 4. Similar strategy, or exact same directions. We're still going to use a table to try to approximate a value of a limit. So in this case, though, we've got a slightly different situation. So in this case, when x is less than 2, let's see. As we get closer and closer to 2 from the left, we go 2.7, 2.75, 2.79. It looks to me like g is approaching 2.8-ish. I'm going to put ish because here it's not really clear what it's approaching. I don't have a nice whole number or anything. Again, it doesn't have to approach a whole number. It could approach something irrational. Just for the simplicity here, I'm thinking about 2.8. So on the left, we're going towards 2.8. On the right side, as we approach 2, it looks to me like we're going negative 3.1, negative 3.01, negative 3.01. looks to me like g is approaching negative 3-ish. Now that's a problem, because that means that on one side we're approaching a positive number, on the other we're approaching a negative number. And so in other words, if we try to picture what this graph might look like at 2, we have from the left that g is approaching 2.8, and then from the right that g is approaching negative 3. Unfortunately, that means that there's nothing in there. So imagine as we look, there, the limit does not appear to exist in this case. And in fact, our limit for g of x as x approaches 2 does not exist. Let's take a look next at question number 9. Question number 9 is a problem that typically appears on the exams every year. It's just a very common type of question of limit to evaluate. But unfortunately, this one isn't as algebraic, and in particular, it's definitely not a direct substitution limit. So here's our thought process. First, if we want to evaluate this limit, as it says, showing any relevant work, boxing our answer, it's important to start, and we'll talk more about why tomorrow or in the next lesson. It's important to begin by taking a look at what happens if we substitute in 11. So for instance, in the numerator, if we plug in 11, we get the absolute value of 11 minus 11, which is 0. In the denominator, if we substitute in 11, we get 11 minus 11, which also equals 0. So in this case, it means that our limit value seems to be doing something like 0 over 0, but unfortunately that's what we call indeterminate. It means that there's more information necessary here for us to go through. We don't have enough information just yet in looking at the form to be able to tell what's happening with this function. So in future lessons, we'll talk about the algebraic techniques we might be able to use, but this one's impervious to algebraic techniques as well. It doesn't work quite as nicely. So my thought is, what would be good would be to get a handle on what this function actually looks like, and to kind of see what we're looking at, and see what the situation looks like. So what I'm going to start with is I'm just going to make a quick little table of values here. So this is just an old strategy learned when I was in, I think, 7th or 8th grade. I think it's probably 7th grade with Mr. Knock, Harriet Eddy Middle School. And I'm going to start by plugging in a couple different values and seeing what's happening on the function. And since our limit is as x approaches 11, I'm going to choose some values to the left of 11 and some values to the right of 11. So in looking here, let's see. X less than 11, let's choose 8, 9, 10. And then on the other side, we'll go 12, 13, 14. And again, you can choose whatever numbers you want. I'm just picking a few representative values here. Now we know at 11 we get 0 over 0, which is basically just a sad panda kind of number at this point. It's not even a number, it's not a value. We don't know what it is. So up here, let's see though, if we plug in 8, we get absolute value of 11 minus 8 over 8 minus 11. When we plug that in, we get 3 over negative 3 equals negative 1. If we plug in 9, we get the absolute value of, 11 minus 9 over 9 minus 11, which equals 2 over negative 2, which equals negative 1 again. If we plug in 10, I think you can probably predict what's going to happen. We're going to get negative 1 as well. So what that means is if we try to picture what this graph is looking like, around 11, let's say 11 is right there, all the values less than 11 appear to be equal to negative 1. So now on the other side though, let's see if we get the same behavior, because if we do, it'd be fine. We could have just a single hole and everything would be good to go. If we plug in 12 though, we get the absolute value of, so I do this right, 11 minus 12 over 12 minus 11. That's equal to 1 over 1, which is positive 1. So we don't have the same y value this time. If we plug in 13, we get the absolute value of 11 minus 13 over 13 minus 11, which is equal to 2 over 2, otherwise known as 1. And if you go through and evaluate the same thing at 14, you're also going to get positive 1, which means to the right of 11, we don't have negative 1 any longer, we have positive 1. So in this case, we now have positive 1 as our value, whereas down below, for those smaller values, we seem to be moving towards or always equal to negative 1. Unfortunately, this presents us a problem. We're supposed to evaluate the limit as x goes to 11 of that function was equal to, but from one side we go to a negative 1, from the other side we go to a positive 1. What that means, of course, is that without any consensus, we unfortunately have to say that the limit as x goes to 11 of the absolute value of 11 minus x over x minus 11 is equal to nothing. The limit doesn't exist. Like that famous line from Katie Heron in Mean Girls, limit does not exist. Now, what's interesting here is obviously there's really finite, interesting, real behavior that we could be looking at. We could look on the left side and say that it's clearly going towards y equals -1, or we could look on the right side and say that it's clearly going towards +1. That's where the one-sided limits will come in, that we'll be talking about in the next few days, and that you probably talked about a little bit last year in pre-cal. So just know it's another option that's out there. So, tough question, but one that I think you should be prepared for. The last thing I'll leave you with before we look on to our next question is it might be worth reminding you that this function, if we think about what that actually describes down below also, this could be written as a piecewise function. Obviously, we can see that there are issues at 11. So when x is greater than 11 or x is less than 11, we have issues. It's clearly undefined at 11, but specifically if x is less than 11, we specifically have y values of -1, whereas if x is greater than 11, our y values are all +1. So we could, of course, look at it as this function as well, as a piecewise function if that helped you more, and you could attack it from there. Okay, that brings us to question number 11. 11 isn't a difficult one to do, but sometimes people look at it and they instantly start to think that the problem's harder than it is. So in looking here, we're given a piecewise function. We've got a parabolic portion and a linear portion. The boundary is at x equals 5. And so people immediately start to look at what's happening around 5, thinking that, well, that boundary is the most interesting part of the function. Unfortunately, in question number 11, they're asking us to limit as x goes to 7. So in this case, if we want to evaluate this limit, we need to use the appropriate branch that includes 7. And looking in here, 7 is greater than or equal to 5, which means that we're going to use the bottom branch. That bottom branch is 6x minus 1, so I'm going to plug 7 into 6x minus 1, which gives us 42 minus 1, or 41. So the moral of the story on question number 11 is make sure you read the question carefully, make sure you look at what the x value is that the limit's approaching. Maybe it might not bite you now, but it could bite you on an exam or something even more with even greater stakes later on. So in this case, all it was about was identifying which branch to use from the piecewise function. Okay, that brings us to question number 12. Question number 12 is one that we've addressed in class, but I want to talk about it one more time just in case that concept didn't stick with you. And it's a particularly unique type of piecewise function. In this case, you're asked to evaluate the limit as x goes to 3 of a piecewise function that has an exponential portion and a linear, in fact a constant portion, but these aren't for x less than 3 and greater than 3, it's for when x equals 3 and when x does not equal 3. And in here, this is always an interesting one for people to get used to. Strangely enough, even though it says x does not equal 3, the answer actually comes from using whichever portion of the piecewise function has x not equal to 3. So in fact, this limit would be equal to pi. Now, as a quick refresher on why it is that pi is the answer here, it's worth reminding you of what this function is saying. Because remember, with limits, we're trying to describe the general behavior. What's happening? Like, what's the consensus? Not what's happening at a single point. One strange thing doesn't actually change the rest of the behavior. So in looking here, let's see what it says. It says that in our function, when x equals 3, 3 to the x plus 5 is how the function behaves. So I'll give you a quick little sketch of our function here. I'm going to attempt to at least. So when x equals 3, we have 3 to the x plus 5. That's going to be 3 to the third, which is 27, plus 5 is 32. So at that point, or on our graph, we have the point 3, 32. Now that's when x equals 3. When x doesn't equal 3, as in when x equals 1, or 15, or -7, or 2/3, or pi plus e, whatever the number might be, we just have y equals pi. Which means for every other value, assuming pi is somewhere like right there, we just have the constant function y equals pi. And with that in mind, what that tells us that if we're trying to describe the general behavior of the function, and like what is the consensus about what this function's doing, all we need to look at is what's happening with all the points, or with most of the points, or all but even in this case, all but one of the points. So notice right here is the only spot, which in fact that is the point, that hole, call it a hole or a point discontinuity, that hole occurs at 3, pi. But as we go towards pi, 3 from the left side, we approach y equals pi, and as we go towards 3 from the right side, we approach y equals pi. So we have a consensus about where everything's going, and that one little outlier point doesn't change the general behavior of the function. No more than in class when we talked about the shirt, no more than that shirt changes color just because of a single dot on there, or a single bleach spot or something. So I typically call these things the general behavior limits. They're a good way to assess whether or not you're comfortable with piecewise functions, as well as whether or not you understand that conceptual underpinning of the fact that limits describe general function behavior. Okay, that brings us to more true-false style questions that talk a little bit about limits and their behavior. So, in this case, no, this isn't. This is not the true-false question. This is just a straight-up question about an even function. So it says in question number 14, let e of x be an even function for which the limit as x goes to 8 of e of x equals 4. Find the limit as x goes to negative 8 of e of x. Explain your reasoning. Now this one's a little tough. It's going to be hard to, we're not going to be able to formally prove everything, so it just says quick little explanation. But the important thing is to remind you what an even function is, and what an even function does in particular. So if e of x is even, let me remind you that that tells us about a particular type of symmetry of the function. Actually, I'm not going to use colon. If x is even, or e of x is even, that means that when you plug in the negative of an x value, you get the same y value as if you plugged in the positive. For instance, an example. A function that is even would be y equals x squared. If you take negative x squared, you get positive x squared. That tells you that we have an even function, and specifically, the graph of that function is symmetrical, or symmetric, about the y-axis. So it's the same y value all the way across. Forgive the fact that I'm not the best drawer. So with that in mind, we're being told something about a function, an even function, and we're told something about its general behavior. What that should tell us is that because the function's even, the general behavior on the right side at positive 8 has to be the same thing as the general behavior on the left side at negative 8. And what that tells me then is that the limit as x goes to negative 8, almost wrote infinity, of e of x has to be equal to the same thing as the limit as x goes to 8 of e of x, which means it's equal to 4. And so there we have it. So again, it doesn't matter that we're talking about a limit, because the general behavior on the right side, whatever it is, has just been reflected to the left side. And it has to match the exact same way because the function's even. So there we go. There is our answer to 14. Likewise, in question 15, we pull the same kind of trick. This time, though, we're talking about an odd function, d of x, where the limit as x goes to 5 of d of x is equal to negative 10. Thinking about the same kind of breakdown and the same process, let's think about what it means. So if the function d of x is odd, that means that there's a different type of symmetry this time. It means specifically that if you plug in negative x to d, as in you try to look at what's happening at the negative of a particular x value, you get not just d of x, but you get specifically negative 1 times d of x. So this creates what we'd call a rotational symmetry of kinds. And in order to see that, let's use a very simple example to work with. I'm going to go with x cubed. It's a classic and classy odd function. Particularly, if y equals x cubed, then if you plug in negative x, in other words, you cube negative x, you get negative 1 cubed times x cubed, which is equal to negative x cubed. And what that produces, of course, is a shape that we've seen many times before. Whatever we have on the positive side, let's make sure I draw this accurately. Whatever we have on the positive side is rotated around the origin, or revolved around the origin, and it's moved to the other portion, into the other quadrant, opposite quadrant. So in this case, we end up with, instead of having the point 1, 1 on our original function y equals x cubed, we have the point negative 1 on our other side, on the opposite side. I guess you could also call it a double reflection. It's a reflection across the y-axis and a reflection across the x-axis. So with that said, what does that tell us? Well, let's think about this. If we want to know the limit as x goes to negative 5 of d of x, that's going to be equal to the limit as x goes to 5 of negative d of x, because that's exactly how these things are equal to, because we're looking at the negative value, we're looking over there, and then with that in mind, we had negative 10 before, so we're now going to have negative times negative 10, which is equal to 10. So there it is. Again, even and odd functions, maybe not the first thing that you remember from pre-cal or your analysis work before, but an important type of function that can come up all sorts of places, and knowing how that symmetry works will pay off many times this year. Okay, that brings us to the true or false questions as promised earlier. The first of those, true or false, where each of these it says to state whether each statement is true or false. Could have fit the word state in there more. Then explain the reasoning. So in this case, the first question we have, 16, or first statement, reads, if f of 1 is 11, then the limit as x goes to 1 of f of x is equal to 11 also. This statement is very vehemently false, but it's one of those tricky ones. It's trying to bait you into thinking that the general behavior and the specific point have to align, and the truth is they do not, specifically because there could be some sort of removable discontinuity here. There could be lots of things that happen in this case, actually. So, if f of 1 equals 11. So let's say this is at 1, and this is at 11. The question is, if that's true, does the limit necessarily have to equal 11? Well, of course, the limit could equal 11. There's no reason to say it couldn't. But it also could just as easily be equal to something else. So for instance here, the limit would be equal to something much less than 11 because of the fact that there's a removable discontinuity occurring right at x equals 1. On the flip side, with this particular setup, we could actually have something else happen entirely as well. We could start with the same piece, but we could actually have a non-removable discontinuity at this point. Again, we'll talk about what that means. It's called a jump. We'll talk about them later. But we could have where the behavior is moving towards one value on the left, but specifically at 11, or specifically at x equals 1, it includes the y value of 11, but then it does something else entirely otherwise. So unfortunately, both of those two situations are possible, which means that this statement is absolutely false. And if you're looking for kind of a quick tagline to remember that, you can kind of think of that shirt example we talked about in class. You could also point out that a specific point does not guarantee any general behavior. And now when I say this, or when I write this, it is true that there is a possibility that that function value would guarantee that there's a limit, but it's for a specific type of function. Specifically, if the function f was guaranteed to be continuous, then this would be true. And we'll see later this week, or later on in this unit, that the definition of continuity actually guarantees that piece. Okay, that brings us next to question number 17. In question number 17, or the true or false statement question in number 17, it says, if limit as x goes to 9 of g of x equals 44, then the limit as x goes to 11 of g of x minus 2 equals 42. So now I think what this comes down to, what's at the heart of this question, is what is the difference between the behavior of g of x and g of x minus 2? Like, how are those two things connected, and how can we take advantage of that connection to figure out what the y value should or shouldn't be? So specifically here, like, there's lots of strategies to attack when you go into this problem. My first strategy is just to think about specifically what happens to the function. So specifically, when you plug x minus 2 into a function, g of x minus 2 specifically shifts g of x 2 units to the right. And the reason this is so essential to think about is it means that what's happening at x equals 9, or around x equals 9 on g of x, is the same as what's happening on x equals 11 on g of x minus 2. So from my end, what this tells me is that if the limit as x goes to 9 of g of x is equal to 44, then when we shift 2 units to the right, the limit as x goes to 11 of g of x minus 2 can't be equal to 42, it has to be equal to 44 also. And what that tells me is that this statement is false. And specifically our reason is that the limit as x goes to 11 of g of x minus 2 is going to be equal to the exact same limit we had before, which is 44. So that method relies almost completely on limits, on function transformation and parent graphs and thinking about how that works. There's also another way to do this called using a counterexample. So specifically, I'm going to come up with, to start, since this statement says if the limit as x goes to 9 of g of x equals 44, so if that's true, I just need to find a g of x where the limit as x goes to 9 is equal to 44. So I'm going to choose g of x equals, let's see, we want something that has a 9 in it. Let's go 4x plus 8. So what did I do? I just came up with a linear function. My thought is that if we plug in 9 to this function, we should get 44. And then, of course, it'd be nice and we'd be able to work with the rest. So specifically, let's make sure I did this correctly. We have 36 plus 8 is 44, so that's good. And lines are nice and continuous. Again, we'll talk about that later, but lines are nice and smooth and continuous. They don't do anything weird. So that's a good sign. So we have a function whose limit is 44. So specifically, the limit as x goes to 9 of g of x is equal to 44. So that's set. So now we know that's true. We've come up with a situation where this is true. Now let's check, is the limit as x goes to 11 of g of x minus 2 equal to 42? So to do that, let's see what happens. So g of x minus 2 is going to be equal to 4 quantity x minus 2 plus 8. Since we're here, and this isn't too bad, we can distribute that out. We'll have 4x minus 8 plus 8 is equal to 4x. And now we're supposed to check the limit as x goes to 11. So let's see. The limit as x goes to 11 of g of x minus 2 is equal to the limit as x goes to 11 of what we saw is equivalent to 4x. And naturally that limit equals 44. And unfortunately 44 and 42 are not the same number. So that tells me that this statement is definitely false. And we've proven a counterexample. We've given a situation where the limit as g of x, as x goes to 9 of g of x equals 44, but the limit as x goes to 11 of g of x minus 2 does not equal 42. And if there's even a single situation where the statement is not true, that makes it a false statement. So voila, there it is. A tough problem, but you can see that there's a couple different strategies to take. A very conceptual one that relies on graphical transformation, and one that just involves finding a function and going from there. And I've seen really good success with that latter method. I think it's a good mathematical technique to go through. Next, that brings us to question 18, the final true-false question we're going to look at. It says, to state whether each statement is true or false, then explain your reasoning. So in 18, it says, if f of c is undefined for value x equals c, then the limit does not exist. And this statement, I will tell you right now, without any investigation first, this statement is very much false. And our reasoning is this. When we look back and think about what it means to be defined or undefined at a particular x value, that does not change the general behavior of a function. Just right off the bat, I could quickly draw out a function. Let's say this is x equals c. I can draw this as my function. Let's say that this is L. If we were to look at the limit at this point, from both the right and the left side, we are approaching the same y value. So we would say that the limit as x goes to c of f of x is equal to L from looking at our picture. Again, assuming that it comes straight across. Not the best drawer. But in here, clearly, f of c is undefined. And by undefined, I mean that there's no y value corresponding to it. We just have a hole or a point of discontinuity right there. There's no other spot where we have a y value establishing that value of f of c. So in fact, this is false by simple counterexample. You could even use the same recognition or statement that you did when we talked about question 16, that the specific behavior of a function does not inhibit or change or influence even necessarily the general behavior unless the function is continuous. So interesting one to think about, but definitely false. Actually, I think all three statements in this case were false to work through. Sorry. Okay, finally, that brings us to question 19, the final one, the big, massive one. We have, in this case, in question 19, we have a huge piecewise linear function with some strange behavior happening. Our job is to take that graph and then find some values or state why they do not exist. And I'm not going to belabor the point here. I'm just going to work through them and talk about them as I go through until we get to the slightly tougher ones at the very end. So first and foremost, 19a asks us to find f of negative 3. And again, this is a graph of f of x that we're looking at over here. So f of negative 3 is going to be the y value when x equals negative 3. Looking into our picture, yes, we do have what's called a jump. There's a big issue here. Like the limit doesn't exist at negative 3. But the full circle or the full dot up there is where we're looking. And that thing occurs at 5. So f of negative 3 is equal to 5. Doesn't matter that on one side it's not there, or it's not defined nicely, or it's not smooth or continuous. We can still find the function value. The next question, though, asks us, what is the limit as x goes to negative 3 of f of x? In this case, we're approaching one y value from the right, positive 5, and we're approaching another y value, which I think is negative 2 from the left, and that means that this limit does not exist, at least not at negative 3. So we're approaching two different values. And approaching two different values is not how you get a nice limit. So third, question 19c. We have the limit as x goes to -2 of f of x. So -2 of f of x. So in looking here, f of x, -2, I can't really tell where it is. I mean, it looks like it's right there. I'm not sure exactly what that is. So to do that, I'm going to have to think about what the behavior of the function is on that interval from, what is it, -3 to -1. So worth pointing out, for -3 less than x less than 1, -1, f of x is a line segment. And exactly how we get there, our line segment, f of x, we can use point slope form. We can actually use one of those points. I'm going to use this as my point of context. And when I say point slope form, I mean y minus y1 equals slope times x minus x1. Basically what I'm going to do is I'm going to write the equation of the line and then plug in -2 and see what it's doing. Because I can see it's nice and continuous. There's no weird things happening between -3 and -1. I just don't know what the specific y value is. So f of x, let's see. The y value down there at the point is -1, 0. So f of x, or y, minus 0 is equal to the slope. Let's see our slope. We're going down 5 and over 2. So our slope is -5 over 2 times x minus a -1. So specifically, we can see that f of x has the line. In fact, I probably shouldn't have used f of x here. I should have just written y for simplicity. F of x is going to be equal to -5/2 x plus 1. Now we want to figure out what the limit is as x goes to -2 there. So that limit as x goes to -2 is going to be the same thing as the limit of -5/2 x plus 1, because that line is what describes the behavior of the function on that small interval containing -2. And if we plug in -2 there, of course we don't have to simplify. That could be an acceptable answer, but just for clarity's sake, we get -5 over 2 times -1. Do that right? Oh, go figure. That's going to be equal to 5 over 2. So it says it should be going through and crossing about 2.5. That looks pretty reasonable to me. I'll accept that and say that that's probably an accurate answer. So there we go. Not an easy one. I'd say this is one of those little skills. It's basically simple algebra or math 7 kind of stuff, but the kind of thing that can kind of mess you up if you're not careful. Okay, that brings us to 19d. It asks us the limit as x goes to 2 of f of x. Looking up here, as x approaches 2, we have all the y values from the left approaching y equals 3, and from the right, all the y values approaching y equals 3. Since they're going to the same place, the limit value is going to be equal to 3. Now keep in mind, this value down here, f of 2, which is actually e in our question, f of 2 is equal to -4, but remember, one specific point doesn't necessarily influence the limit. So in this case, the limit didn't actually give us what we were looking for. So we finished it, and we just found the limit separate from the function value. And then last straightforward question here. It asks us the limit as x goes to infinity of f of x. Now we're going to focus our attention on infinite limits, or limits at infinity later on in this unit. But for the moment, you can think of this as just describing what's happening with the y values as x continues getting bigger and bigger, based on our picture, of course. And in looking up here, I see a horizontal line starting at x equals 3 and just continuing on to the right at y equals 4. That tells me that y equals 4 is what the function's y values are getting closer and closer to. So based on all I can see in this picture, I'm going to go ahead and say that that limit as x goes to infinity is just positive 4. So interesting, but again, we'll talk about that in more depth later on. Finally, that brings us to the last two questions here that we're going to look at, g and h. These are a little bit more involved here. So first with g, it says let t of x equal f of x minus 10. Find the limit as x goes to 13 of t of x. So we've talked about this before. So we talked about this with that true or false question a little ways before. I think it was right here, 17. So in this case, as we look, we've got to think about what the function values are doing, or what part of the graph are we looking at. So x minus 10 takes f of x 10 to the right. So in other words, wherever we started 10 units, or blah, 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 blah. In other words, we want to look at the original graph of f, which we have, which by the way only goes from -5 to 5. So we're pretty limited on what we can offer here, or else we just can't do much. But it wants to limit, let's see, it wants to limit as x goes to 13 of f of x minus 10. So let's play this for a second. So that's what we're being asked to evaluate. So we've done this before. The limit as x goes to 13 of f of x minus 10, that shifted graph, is the same thing as the limit as x goes to 3. Specifically, it's the limit as x goes to 13 minus 10 of f of x. So with that in mind, we really want to evaluate what is the limit as x goes to 3 of f of x, because that's going to describe the behavior of the function that we're looking at. And in fact, looking up at our picture, if we want to know what's happening up here on our graph, as x approaches 3, from both sides y is approaching 4, which means this limit is equal to 4. And so it's the same thing for our function t of x, the transformed version f of x minus 10, that would be approaching 4 as well. Now with that said, if you look at my solutions, there are a couple different ways that we could go about doing this. There's lots of different ways to get here, so you can see some other techniques involving some substitutions and things like that. But again, a nice graphical kind of conceptual approach is a really nice way to go too. Finally, that brings us to our last question, question H. It says, let h of x equal this piecewise function. We have f of excuse me. We have f of x for x less than 1. We have 2x for x greater than 1, and we have 5 at x equals 1. And they want the limit as x goes to 1 of h of x. Now, technically, this is a little bit beyond our pay grade based on the first lecture of the course, but for the moment, I think it's worth just thinking about what this is telling us and what this all means. So in looking in here, what I've got to think about is what's happening on the left and the right of x equals 1. In a sense, if we're talking about the limit, that 5 doesn't even matter. It doesn't even matter at all what's happening. So let's think about what's happening with h in the other cases. So as x, let's see, if x is greater than 1, then h of x is approaching 2 times 1, or 2. The reason I say that is, of course, 2x is the function when x is greater than 1. So you could almost imagine we could graph this picture out. So here's x equals 1. It says 2x. So there's what's happening. And of course, we do have that 5 that's in there. Likewise, it says the function h of x is f of x when x is less than 1, which means if we look at our picture here, we could actually sketch what the rest of this looks like. So there is our function itself, like there is the graph of h of x that we're looking at. But specifically notice, at x equals 1, it looks to me like f of 1 is equal to 2. And in fact, if we actually found the equation of that section, we'd get that f of x is equal to x plus 1 on that interval that contains 1. So in fact, it looks like from the left and the right both, we're approaching the same y value. So in fact, if x is less than 1, h of x approaches f of 1, which is equal to 2 also. Since both the left and the right side approach 2, or from our picture we can see it as well, that tells me that the limit as x goes to 1 of h of x is going to be equal to 2 as well. And again, I'd almost consider that kind of a plus question, lots of different little things to do in there. But again, hopefully this was helpful and informative. Hopefully this has helped carry you through that first lesson and the first assignment of the course. Have a good night.